Good afternoon, class. We are looking at College Algebra Chapter 9, Sequences and Series. Here, Section 9.1, Sequences and Series. We are going to cover 9.1, Sequences and Series, 9.2, Arithmetic Sequences and Series, 9.3, Geometric Sequences and Series, and we're going to finish it with the binomial theorem. The objectives are: write the terms of a sequence defined by an explicit formula. Write the term of a sequence defined by a recursive formula. Use factorial notation. So let's remind everybody of what we've done. Conics, circle. A circle is the set of points in a plane that are the same distance, called the radius, from the fixed point called the center. X squared plus y squared equals r squared. If it's centered at 0, 0, x minus h quantity squared plus y minus k quantity squared equals r squared. If it's centered at h and k. An ellipse is a set of points in a plane. The sum of whose distances from two fixed points is a constant. The length of the measure axis is 2a or 2b, depends whether it's elongated along the x-axis, 2a, along the y-axis, 2b. The two fixed points are called the foci. Each is a focus of the ellipse. F1 and F2 represent the two foci of an ellipse. The formulas are x squared over a squared plus y squared over b squared equals 1, if it's centered at 0, 0. X minus h squared over a squared plus y minus k squared over b squared equals 1, if it's centered at h and k. If a is larger than b, it's elongated along the x-axis, then c squared is a squared minus b squared. And if b is larger than a, c squared equals b squared minus a squared. I like to keep the a squared under x squared and b squared under y squared regardless. And the area is pi times ab. So P is a point, any point on the ellipse, having coordinates x and y. Pf1 and Pf2, they add up to a constant. That constant happened to be 2a. Here's the hyperbola, class. A hyperbola is a set of points in a plane, the difference of whose distances from two fixed points called the foci is a constant. For every point on the hyperbola, the difference m minus n is the same constant. In other words, pick a point P and connect it to focus 1, focus 2. Their difference is a constant. A hyperbola has two vertices. It may be that it opens sideway, and the vertices, if the center is at 0, 0, or the x-intercepts, if it opens up and down, would be the y-intercepts. Vertices. The vertices are the points where the graph crosses the x or y-axis. Center, the point halfway between the two vertices, is the center of the hyperbola. Transverse axis, the line through the vertices, this line, which happened to be the x-axis in this graph, is called the transverse axis. Formulas is similar to elliptical formula, but with a negative in between. X squared over a squared minus y squared over b squared equals 1. Y squared over b squared minus x squared over a squared equals 1. Where a squared and b squared is equal to c squared, always. It is such that a and b are always less than c. Asymptotes plus minus b over a times x. Pay attention to the way I'm writing this. I keep the a squared under x squared in this case and in this case. This one opens sideways to the right and left, and this one opens up and down. When you keep them in the same format that I have it, then the equation of asymptotes remain unchanged. Otherwise, they do change, as it happens in many texts. Of course, if the center is at h and k, then the formulas change accordingly. And this is known as fundamental rectangle. When you connect the diagonals, give you the two asymptotes. Parabolas. Equation of a parabola where vertex is at 0, 0, focus is at a0, a is larger than 0. The equation of a parabola with vertex at 0, 0, focus at a0, and directrix x equals minus a is larger than 0, is y squared equals 4ax or 4px. I'm going to discuss the a and p with you in a moment. So it opens up or down. The vertex is at 0, 0. And as you recall from algebra, from intermediate algebra, y equals ax squared. When a is positive, it opens up. When a is negative, it opens down. And if you solve for x squared, becomes it's in the form of 4py or minus 4py in this case. I like to go with p, as some texts they go with a, because I want to distinguish between this a that we learned in algebra, in intermediate algebra, and this p, which is the focal distance. This opens sideways to the right and to the left. So again, we have the vertex at 0, 0. However, this time x is equal to ay squared. Notice this is quadratic with respect to x because it opens up and down. This is quadratic with respect to y because it opens sideways. So if a is positive, it opens to the right. If it's negative, it opens to the left. And so the equations become y equals 4px or y equals minus 4px. What we need to know is this focal distance that is called either p or a, but I'm going to stick with p. The distance that you see here, this distance is equal to this distance, is called the focal distance. I would rather go with 0p. So y squared is 4px or minus 4px. X squared is 4py or minus 4py. It depends whether it opens sideways or up and down. Now, the relationship between a focal distance and this a in algebra is that p is 1 over 4a or a is 1 over 4p. Lattice rectum. The lattice rectum of a conic section is the chord, the line segment, through a focus parallel to the conic section directrix, and it has the size of 4 times p. The length of the parabola's lattice rectum is equal 4 times the focal length. For p. Lattice rectum, its endpoints lie on the curve. So take a look at the concept. So here's the F. So the line parallel to the directrix cuts the graph at 2 points. Those are the end points. Now we want to prove that this distance is 4 times this distance, which is a focal distance. The distance from the focus to the vertex is equal to the distance from the vertex to directrix. Each one is called the focal distance. So as we look at this graph, we see that here's the proof, everybody. By definition, the distance from focus to any point P on the parabola is equal to distance from P to the directrix. If you look at the definition of the parabola. So pick a point, connect it to the focus, drop a perpendicular to the directrix. The two distances must be identical. So PD is equal to PF. That's by definition. Therefore, this distance is equal to this distance. And we know this distance is P, therefore this distance is P, therefore this distance is 2P. So this is 2P, this is 2P. So this becomes 4P. That is the proof, everybody. And now let's go to new stuff, everybody. Section 9.1 sequences and series. Measurements collected at discrete time points and quantities that undergo periodic changes, such as annual plant or insect populations, are studied using the concepts of sequences, the data and difference equations, the description of the mechanism of change. A sequence is a list of numbers written in a specific order, a sub 1, a sub 2, all the way to a sub n, and it continues. It is a real valued function f whose domain is the set of natural numbers, whether natural numbers 1, 2, 3 to infinity. We use the notation a sub n to denote f of n, a sub 1, a sub 2, all the way to a sub. The first term is a sub 1, the second one is a sub 2, and the general term, we call it a sub n, everybody. Recursive sequence, also called difference equation. A recursion or recursive formula defines a sequence by specifying the first few terms of the sequence and using a formula to specify subsequent terms in terms of preceding terms. The next term depends on knowing the previous one or previous ones. The format is a sub n plus 1 is f of a sub n. We will discuss these sequences, arithmetic and geometric sequences later on, but just to give you an idea, something that you have seen before, I want to remind you. So there's really not much to sequences. You've already seen that. For example, an arithmetic sequence that we will discuss later on is in the form of a sub 1, a sub 1 plus d, a sub 1 plus 2d, and so forth. So where the difference d, or distance they call it, is a difference or distance between consecutive terms is constant, can be defined by a sub n plus 1 is a sub n plus d. This is recursive. Or explicitly by a sub n equals a sub 1 plus n minus 1 times d. Example 1, 5, 9, 13. I hope you notice this is the first step. If you add 4, or simply, so add 4, you get to the next one and the next one. So there's a constant. And that's actually the proof, because you're adding a constant. Similarly, a geometric sequence, a sub 1 times r, a sub 1 r squared, and all the way to a sub 1 r to the power of n minus 1, where each term is r times the previous one, can be defined recursively by a sub n plus 1 is r times a sub n, explicitly by a sub n equals a sub 1 r to the power of n minus 1. Example, 1, 4, 16, 64. Notice if I multiply by 4, I get 4. Multiply by 4, I get 16. Multiply by 4, I get 64, and you move on in the same direction. So that's, you have a constant that you are multiplying it by. Now, given the general term, find the first 5 terms. For example, a sub n equals n. This is very simple. All you have to do, choose n from the natural numbers, 1, 2, 3, and continue. If n is 1, becomes 1. If it's 2, becomes 2. If it's 3, becomes 3. So this is very simple. 1, 2, 3, 4, 5. Why do we stop at 5? Because it's asking for 5 terms. First 5. First 5 terms. Now, if n is 1, you get 1 over 1 plus 1 or 1/2. If I go with 2, then I have to put 1 plus 2. I get 2/3. If I put 3, I get 3 over 4. 4, 4, I get 4 over 5. And so those are the first 5 terms. D sub n, the digit in the nth decimal place of a pi. We want to come up with that, everybody. And to do so, Notice pi is not 3.14. So what is pi? 3.141592 continues indefinitely. Continues indefinitely. And that's the idea. So, for example, the first place would be 1 because we want the nth decimal place. The second decimal place would be 4. The third decimal place would be 1. The next one is 5. The next one is 9. The next one is 2, and so forth. We just want 5 of them. So 1, 4, 1, 5, and we stop at 9 because we just want the first 5. Find the first 5 terms of this sequence. A sub n is 2 to the power of n minus 4. We start with 1. 2 to the power of 1 is 2. Minus 4 makes it negative 2. The second one, 2 squared minus 4 is 0. And just as an example, I do one more, but the thing is, as long as you can do a couple of them, that's it. If I want the next one, I'm going to call it a sub 3. So 2 cubed, which is 8 minus 4, which is 4. And I'm going to leave it for you to find the other two in the same manner. And we're going to write it. It's a good practice to put everything together. So we have negative 2, 0, 4, 12, 28. We just wanted the first, again, 5 terms. The idea is that if you can come up with 5 terms, you can come up with easily with more terms. It's not a big deal. Now let's go back. We want to find the formula for the general term if a few terms are given. And what you do whenever you find the general term, you really check it. So if we look at the first one, we notice that the denominators are 2, 3, 4, and I can put the denominator here 1. Okay, so that's easy to see that the denominators are 1, 2, 3, 4, so you can just go with n. And the numerators, if you look at the numerators, we have e to the power of 2, to the power of 3, to the power of 4, and this is e to the power of 1. So it's e to the power of n over n. And again, definitely check. How do you check? Very simple. If n is 1, do you get e? If n is 2, do you get e squared over 2? If n is 3, do you get e cubed over 3? This is how you check it, and you must check everybody. We go to b, and we notice that the numerator doesn't change. The numerator is 1, so the answer is 1. But what about the denominator? This one has 3, this one has 9, this one has 27. So 3 means 3 to the power of 1, 9 means 3 squared, 27 means 3 cubed. Can I put a 1 there and call it 3 to the power of 0? And the answer is yes. So what is the general term? It's a fractional format, just as this one. The numerator is fixed at 1, and the bottom has 3 with some exponent. What exponent? 3 to the power of n minus 1. Please pay attention to this concept of checking. If I put n equals 1, I get 3 to the power of 0, which is 1. If I put 2, I get 3 to the power of 1, which is 3, so 1/3. And if I put 3, I get 3 minus 1 or 2. 3 squared is 9, so 1 over 9. So you must check. 1, 3, 5, 7. Clearly, the next one is 9. We are dealing with odd numbers. Now, the way you represent odd numbers, you can represent 2n minus 1 or 2n plus 1. I want you to know that. However, you have to check. There are 2 ways. I want to make sure that you know that odd numbers, we can represent them with 2n plus 1 also, okay? However, you have to check. If If you choose n to be 1, you get 2 times 1 is 2 minus 1 is 1. 2, 2 times 2, 4 minus 1 is 3. 3, 2 times 3, 6 minus 1 is 5. But over here, the first one, 2 times 1 plus 1 is 3. So we missed the first one. So this one does not work. And that's the idea. Check and recheck. So this is 1. Then we go to 4, 9, 16, 25. We notice we are squaring natural numbers. So 1 squared is 1, 2 squared, 3 squared, 4 squared, 5 squared. So square of numbers. So that must be n squared. Now, in this case, there are a couple of things we notice. First and foremost, the denominator is 1, 2, 3, 4, 5. Again, the denominator is n, just like the first one. And the sign is, the numerator is 1. So it's really, it's easy to see it's 1 over n. However, there's one thing that is interesting to notice. This is positive, this is negative. This is positive, this is negative. So they alternate in sign. It's called an alternative sequence. So if you ignore the sign, the answer is 1 over n. But when it comes to the sign, negative 1 to the power of n is used, or negative 1 to the power of n1 to represent alternative. So which one do we use and why? If I use this one and n is 1, I get negative 1 to the power of 1, which is negative. So the first one is positive, so that doesn't work. If I use this one and n is 1, minus 1 squared is 1. So that means positive. The next one, if I use 2, 2 and 1 is 3, minus 1 cubed is negative. That works. So I get minus 1 to the power of n plus 1, because the first one is positive, the second one is negative, and times 1 over n. This is because of the alternative nature of the sequence. However, if this was negative and this was positive, I had to use this one. So pay attention to the use of negative 1 to the power, which one and why. By the way, in some texts, instead of n plus 1, they may use n minus 1, and it has the same effect as n plus 1. Again, difference equation. Sequences are sometimes created recursively, specifying the next term given the present term. The initial term of the sequence must also be specified. This procedure defines each new term as a function of the previous one. And it may not always be possible to determine the general term of the sequence algebraically. A difference equation, also known as recursive sequence, is an equation of the form we've already discussed, that a sub n plus 1, or f of a sub n, where a sub 1 is given and f is a real valued function. A solution is a sequence a sub 1, a sub 2, all the way to a sub n, satisfying the given difference equation. That's a definition. One such sequence that you're familiar with is called Fibonacci sequence. As you recall, if the first one is 1, the second one is 1, then the next ones add up. So this is 1, there is nothing to add up. This is 1, but now you can add these 2, you get 2. Add these 2, you get 3. Add these 2, you get 5. These 2, you get 8. These 2, you get 13. These 2, you get 21. So if I want the next one, just as an example, what do? I add these 2, and I get 30. And this continues, okay? Example in nature. The number of branches increase up tree trunk according to the Fibonacci sequence. So the first year you have 1, the next year you still have 1, and then the next year you add up to 2, the next year they add up to 3, and so on and so forth. They happen a lot in nature, the concept of the Fibonacci sequence and golden ratio, if you Find the first 6 terms of the recursive sequence. All right. The first one is 6. And so we want 5 more. So if I choose n to be 1, the next one, so if I choose n to be 1, okay, I get a sub 2. So this is a sub 1 over 1, which is 6. Again, replace the n with 1. If you replace it with 1, you get this one. Let's replace it with 2, everybody. If I replace the n with 2, I get a sub 3. So a sub 3 is a sub 2 divided by 2, which means 6 divided by 2, it's 3. Let me show you a sub 4 quickly. If I want a sub 4, it's a sub 3 divided by 3, which is 3 divided by 3, which is 1. And I'm going to leave it for you to find the other 2, and we're going to write the first six terms. A sub 1 is given, a sub 2 is given. We already have 2 of them, and we want the rest of them. That means we want 4 more. So pay attention to what happens. The next one is a sub 3. So if you choose this one to be 3, that means n is 1. Again, if you set this one equal to 3, n is 1. So you have a sub 3 equals a sub 2 plus 2a sub 1. A sub 2 is 2. 2 times 1 is 2. They add up to 4. Now the next one is 4. If I set this equal to 4 to give me a sub 4, then n must be 2. So this is 2, this is 2, this is 2. A sub 4 is a sub 3 plus 2a sub 2. So again, this one is 4, this one is 2 plus 1, 3. So that basically means if you look at this one, it means if you want any term, pick the previous one. So I want a sub 4, pick the previous one, plus 2 times the one before that, plus 2 times a sub 2. So a sub 3, we found it to be 4. 2 times 2, they add up to 8. Now let's do one more. According to this, basically, again, or go back to this. If you want the next one, so if I want a sub 5, I need a sub 4 plus 2, a sub 3. And I know a sub 4 is 8, and I know a sub 3 is 4. 2 times 4, 8, and 8, they add up to 16, and the next one is 32, and we're going to write all of them. I hope you're following that. So again, if you want a term, pick the previous one plus 2 times the one before that. A sub n plus 1. If you want a term, 2 times the previous one, subtract 4. So we start with, and see, a sub 1 is given. So if I want a sub 2, I want, this says a sub 2 is 2 times a sub 1 minus 4, according to this general formula. 2 times 3 minus 4, 6 minus 4 is 2. I'm going to do one more, and you can figure out the rest on your own. I want a sub 3. That means I have to go with 2a sub 2 minus 4. And 2 times 2, 4 minus 4 is 0. I've shown 2 of them. I'm sure you can figure out the rest. So 3, 2. 3 is the first one. 2 is the second one we found. 0 is the third one we found. And I'm going to leave these 3 for you to convince yourself those are the answers. You can work on it later. We're going to continue with sequences and series. A finite sequence is a function that has a set of natural numbers of the form 1, 2, 3, 2, and it stops at some point. An infinite sequence is a function that has the set of all natural numbers as its domain and keeps on going. So the notation is a sub n or f of n. Convergent and divergent sequences. A convergent sequence is one whose terms get closer and closer to some real number. So they, in essence, they do have a limit. That's the concept. The sequence is said to converge to that number. A sequence that is not convergent is said to be divergent. You'll learn more about this in later courses. Limit refers to the long-term behavior of a sequence, i.e. what happens to a sub n of a sequence in the long term. Notation, the lim of a sub n as n goes to infinity is L. We say that a sub n converges to L. The lim of a sub n as n approaches to infinity is infinity, or negative infinity, or DNE does not exist. We say the sequence diverges. Let me just write this out for you. That's the meaning of it. DNE does not exist. Series and summation notation, summation rules. S sub n, the sum of a sub 1 plus a sub 2 all the way to a sub n of the first n terms of a sequence, a sub 1, a sub 2, and a sub 3. This is sigma. Capital sigma is the Greek letter sigma and indicates a sum. The sigma notation, the summation I going from 1 to n of a sub I, means add the terms a sub I beginning with the first term and ending with the nth term. I is called the index of summation. A finite series S sub n is a sub 1 plus a sub 2 all the way to a sub n. And we write this as summation of a sub I as I goes from 1 to n. An infinite series S, and normally we use S sub infinity, is a sub 1 plus a sub 2 plus a sub 3, and it goes to infinity, is summation I going from 1 to infinity of a sub I. And by the way, you can say a sub j and use j here. So, or sometimes they use a sub k and use k here. So it means the same thing. As an example, let's see what happens to these two cases. By calculating the first few terms. That's the concept of looking at the long-term effect or the limit. Notice if I put n equals 1, I get 1 over 1 or 1. If I put 2, I get 1 half or 0.5. If I put 3, I get 1/3. If I put 10, I get 1 over 10 or 0.1. So what happens? It clearly is getting smaller. The idea is that what happens when the denominator is getting larger and larger, the fraction is getting closer and closer to 0. So the limit, the notation-wise, is limit of 1 over n as n approaches infinity is 0. And we say this is convergent. If we were to graph this, it would give us those points. You may remember the graph of y equals 1 over x, which has two pieces, of course. So this is the graph. So it is convergent, and it converges, and it runs along the x-axis. So y becomes 0, the concept of a horizontal asymptote in rational functions. What happens here? If I choose n to be 1, I get -1. If I choose n to be 2, I get +1. What does it mean? It will always alternate between negative and positive based on the value of n being even or odd. If it's odd, remains negative. If it's even, becomes positive. So B3 is -1, B4 is 1. So the value alternates between negative and positive 1. The limit of -1 to the power of n as n approaches infinity. This limit dne does not exist, and we say B sub n is divergent. When we look at the limit, we want one value and one value only, not infinity, not negative infinity. This oscillates between the two. And if you were to graph it, it looks like that. So this is convergent. This is divergent. What about n squared? That's what I wanted to look at. Well, if I choose n to be 1, I get 1. 2, I get 4. 3, I get 9. And so what's happening? It's getting larger and larger. 4, 16, 5, 25. It's because it just continues indefinitely. It ends up going towards infinity. This is, if I were to write this, I would say the limit of n squared as n goes to infinity is infinity, and therefore is divergent. If we were to write it, with regards to the concept of a limit. Summation properties. If a sub 1, a sub 2, and a sub 3 all the way to a sub n, and b sub 1, b sub 2, b sub 3 all the way to b sub n are two sequences, and c is just some number, some constant, then for every positive integer n, the following is true. The summation of c is n times c. When c is a constant, just write c, and it's going to go from 1 to n. So you're going to write c plus c plus c. How many times? N times becomes nc. If you happen to have c times a sub I, c can come out. If you're adding or subtracting, you can put them into two different formats, okay? So the summation of a sub I plus b sub I is the summation of a sub I plus summation of b sub I, both of them going from I equals 1 to n, or if you're looking at their difference. Summation of I, as I goes from 1 to n, means 1 plus 2 all the way to n. It can be shown that is n times n plus 1 divided by 2. A summation of I squared is, which means 1 squared, 2 squared, all the way to n squared, is n times n plus 1 times 2 n plus 1 quantity squared. And summation of I cubed, which means 1 cubed all the way to n cubed, is really this one to the second power, n squared, n plus 1 quantity squared over 4. We are going to use this for evaluations. All right, so let's look at this one. When they say evaluate, that means come up with an answer, come up with a number. So I'm going to plug in k equals 1, and I get 2 to the power of 1 plus 1. Then I'm going to put k equals to 2 squared plus 1, 2 cubed. I go all the way to number 6. Now, clearly, this is 3, this is 4 and 1, 5, this is 8 and 1, 9, and so on and so forth. And when we add up these numbers, we end up with 132. So evaluation means plug in, work it out. Summation of a sub j as j goes from 3 to 6. So that means a sub 3 plus a sub 4 plus a sub 5 plus a sub 6, and we stop at 6. The upper limit of the summation is number 6. And a is not a number that we know what it is, so we just have to write it in this format. Unless we know what a is, then we can figure it out. The summation of 5 as I goes from 1 to 40, we look at those properties and we see this one means c times n or n times c. So 40, because this goes from 1 to 40, 40 times 5 makes it 200. the summation of 2i as I goes from 1 to 22. According to one of the properties, I can take the 2 out. Then I can use this one, summation of I is n times n plus 1 divided by 2. And here's n. So this 2 remains, and this part is n, which is 22, times n plus 1, which is 22 plus 1 divided by 2. And we can cancel these two numbers. So we have 22 times 23, which is 506. Summation of 2i squared minus 3 as I goes from 1 to 14. We are going to use the properties to separate this from this and take the 2 out. So we can make this one 2 summation of I squared as I goes from 1 to 14. And this one, you can keep the 3 in or out, it makes no difference. This one is 2 times. Now, when you look at this part, you can use 5. So this gives you 2 times n, which is 14, everybody. 2 times n, which is 14, times n plus 1, 14 plus 1 times 2 times n, 2 times 14 plus 1, divided by 6. So that's this one. And this one, we've already used a case like this. N times c, 14 times 3. These two cancel each other. And we get 14 times 15 times 29 divided by 3. This is 5. 14 times 5 times 29 minus 42 results in 1988. All right, we want to write them out. So it's not about evaluation. Just plug in k equals 1, you get 1 over 1 plus 1. Then 2 over 2 plus 1. 3 over 3 plus 1, 4 all the way to n. So that's what they want us to write. Of course, we know this is 1/2, this is 2/3, this is 3/4, that, but that's how they want us to write, because we are just writing out. Same thing here. K is 0. So if I put 0, I get 0 squared minus 1. If I put 1, I get 1 squared minus 1. If I put 2, I get 2 squared minus 1. If I put 3, get 3 squared minus 1, all the way to n squared minus 1. And again, I want you to notice, I didn't write the first one. The first one, if you plug in 0, this zero squared minus 1, which is minus 1. So we should have that here, minus 1. But I believe this is k equals 1 now. You know what? That's what it's k equals 1. It starts with number 1. Now I want to go back, express each sum using summation notation. 1 squared plus 2 squared, 3 squared, all the way to 9 squared. So we should clearly see that this is the summation of I squared, J squared, K squared, whatever you want to call it, as it goes from 1 to n equals 9, from 1 to 9. So the summation of K squared, K goes from 1 to 9. And by the way, you can say I squared. I want to write that because I want to make sure that you understand there's no difference between the two. You could write I goes from 1 to 9. But if you do that, you must write I squared. It's the same thing. You could go with J. All right, what do we notice here is that 1/2 1/2, 1/4, 1/4, 1 over 2 to the power of n minus 1. So this is the general term. And when general term is given, that's all you need to use. So 1 over 2n minus 1. And it starts with what? If you choose n to be 1, you get 1 minus 1, 0, to the power of 0 is 1, and it gives you the first term. So it's the summation of this general term, 1 over 2 to the power of n minus 1, as k goes from 1 to n. N is clear, but as far as 1 is concerned, just you want to make sure that you plug in 1, and it gives you the first one. If you plug in 2, 2 minus 1 is 1, 2 to the power of 1 is 2. If you plug in 3 minus 1, gives you 2, 2 squared. And this is 8, everybody, by the way. Okay. Let me just... Number 8. We want to evaluate this one. First, we're going to take the 3 out to make life easier. And then the summation of k going from 1 to 5, k or I makes no difference. So we're going to use this one 3 times this one. So instead of k, imagine it's I. N times n plus 1 divided by 2, where n is 5, everybody. So 3 is a multiplier. N is 5. 5 times 5 plus 1 divided by 2. So 3 remains. And then 5 times 5 plus 1 divided by 2. And this is 6. And 2 gives you 3. So we have 15 times 3, 45. All right, to do so, we are going to separate this into 2 pieces. The summation of k going from 1 to 10 of k cubed plus the summation of k going from 1 to 10, 1. So we cut them into 2 pieces, okay? And again, reminding you that, for example, this we have been using all along, but this is the property we are using. Now for k cubed, we use I cubed. I cubed is the same as k cubed. So we use that one. And for this one, we use this one. So to do this, we're going to say, and by the way, n is 10, everybody. This is n. N is 10. For this question, n is 10. So this one is 10 squared times 10 plus 1 quantity squared divided by 4. And this one is simply 10 times 1 or 1 times 10. As you know, this is 100. And so divided by 4 is 25. This is 11. Squared is 121. Multiply by 25 plus 10. You get 3025 when you multiply it by 121 and add 10. You get 3035. Here's the last question. We cut this into 3 pieces. Again, using, in essence, this property. So we have this one minus 7 times this one plus this one. So we cut it into 3 pieces. And of course, n is 24, everybody. N is 24 in all of these 3 cases. So this one, k squared, is the same as I squared. We've used that before. So n, and n is 24. So 24 times 24 plus 1 times 2 times 24 plus 1 divided by 6. That's this part. Minus 7, summation of k, we're going to use summation of I, n, which is 24, times 24 plus 1 divided by 2. Of course, we have a negative 7 in front. And this one, we use nc, 2 times 24. So we do the math, we plug in, we do the math, we end up with 4,900 minus 2,100 plus 48, which is 2,848 as the final answer.